Oops. This is an example of an artificial hip. We've learned a lot about the mechanics of how humans work as organisms over the last 100 years or so. How we work as sort of physical objects that have to obey the laws of physics that you know about. We live in a gravitational field, and that affects our day-to-day life. And if you have hip pain or a hip that's diseased in some way, and you can't stand up against that gravitational field in the same way, that severely limits what you can do in the world. And so biomedical engineers have been working for many years on how to design replacement parts for joints like the hip. And the artificial hip is the most well-developed of those. We'll talk about this in some detail. And you can imagine that there are many requirements that a device like this has to meet in order for it to be a good artificial hip. And we'll talk about those and how the design of these has changed over the years and what we can expect in the future. And lastly, up here is a picture of a much smaller device. This is actually an artificial heart valve that is made of plastics and metal and can replace the valve inside your heart. And valvular disease is not uncommon in the world. We'll talk about that a little bit. We'll talk about how your normal valves function inside your heart and how your heart couldn't work in the way that it did if it didn't have valves that were doing a very complex operation many, many times a day. And then we'll talk about how you can build something to replace a complicated small part in the body like that. But let's take a step back for a minute. That's sort of one way of looking at biomedical engineering, by looking at sort of the things that you know about that have been the result of the work of biomedical engineers, and talk more generally. So what is engineering? What do engineers do? What makes engineering different than other fields of study? What makes it unique so that we have a school of engineering at Yale that's separate from science and the humanities? Any thoughts? It's much more hands-on. I mean, you're actually in there doing things. Many of the things I showed you were things that were built, right? That were built from parts. So that's a good description. What makes it different from science? Science can be hands-on. You might be down at the lake, picking up algae and studying them or something. That would be kind of hands-on. But what's different? What would make you an engineer? Yeah.
Engineer designs something and observes.
You design, so scientists observe and try to describe, and engineers try to design. They take those descriptions and that science that's known, and they try to design new things. And so if you look at a dictionary, it has words like this, that you're designing things, or another way to say that is that you're trying to apply science. You're looking at applications. So we're trying to take scientific information and make something new. And the other thing about it is that you could make lots of things that are new, but generally you think of engineers as making things that are not just new, but they're useful, that they do something that needs to be done, and that they do something that improves life, right? The quality of life of people. And so here's a brief and very biased history of engineering. It's short, but engineering became a discipline at about the middle of the 1800s. Lots of universities started teaching engineering as a discipline, including Yale, in 1852, around that time. This might have been the first course that was offered in engineering in the country, was taught at Yale in civil engineering in 1852. And even Yale students don't know this, what a long, distinguished history of engineering that their own institution has. In fact, the first PhD degree in engineering was awarded to a fellow named J. Willard Gibbs at Yale in 1863 for a thesis he did on how gears work or something. I forget exactly what the details are, but have you heard of Gibbs? Is this a name that rings a bell? Where'd you hear about Gibbs from? Sorry? Yeah, G, Gibbs free energy, that annoying concept that you had to try to master in chemistry at some point. But Gibbs is really the father of modern physical chemistry, and was one of the most most famous scientists of the 19th century and got the first PhD in engineering here at Yale. And then from these beginnings, engineers transformed life in the 20th century. So a lot of things started in the 20th century and became commonplace. Things like electricity, having electricity delivered to your home. So you had to have ways to generate electricity and to carry it from point to point. And it was engineers that did that. Built bridges and roads, and we couldn't, and automobiles. And so we can get from one place to another relatively quickly because of that, because there are airplanes that were also developed by engineers in that century. We designed a lot of new materials that could be used to build things that couldn't have been done otherwise. Things like steel and polymers or plastics and ceramics. And, of course, computers, which has progressed remarkably due to the work of engineers in your lifetime. Till now, you can carry around a cell phone, which would have been unthinkable even 30 years ago. So engineers in the 20th century have transformed our society. One of the other things that happened during the 20th century is that human life expectancy increased dramatically. People started living a lot longer. And so what I plot on this graph here is as a function of time, years, dates, life expectancy is a function of time. And what you'll see here is that about for the period before sort of 1700 or so, human life expectancy was less than 40 years of age. So that means a person that was born in that year could expect to live on average about 40 years. That was the expected lifespan. And the expected lifespans increased dramatically in the last couple of hundred years. Till now, for people that were born when you were born, you can expect to live to be 80 years old, a doubling in lifespan, fairly dramatic. So what's responsible for that? Why are people living longer than they did just a few hundred years ago? Well, there's a clue here on the slide. I indicated a couple of points here, where if we looked in the year 1665 in London, you could ask the question, another way to ask the question, why are people living so long, is to ask the question, why do people die? And in 1665, 93% of the people that died in that year died of infectious diseases. Right? In contrast, if you look at a U.S. city 10 years ago, in 1997, for example, then people still died, but they didn't die predominantly from infectious diseases. They died from other things. Only 4% died from infectious diseases. So one of the reasons there's a huge increase in lifespan is because people aren't dying of things that they would have in prior years. So why the change in infectious diseases? Why did I focus on that one? What makes it so much better to be alive now in terms of your likelihood to die of an infectious disease than it did in London in 1665?